Welcome to week 6. This week we're going to talk about exploitation and the various tools that you can use to exploit a system that you have already scanned and identified potential points of entry. So to start out with, we want to kind of do a review, a refresher on vulnerabilities to exploits. So a vulnerability is a weakness of the underlying software or system or something of that nature. So it's a flaw in the design, implementation, or configuration, which could allow some attacker or some malicious individual a vector to get into that system. An exploit is going to be some working code or some method that exploits a vulnerability or triggers the vulnerability. And it could do anything from crashing a system or crashing the service to bypassing authentication. There could be information leakage, code execution. There's quite a lot. And so a lot of you have seen various exploits out there and know of various ones, but those are different than vulnerabilities. And then finally, proof of concept is typically a very small example of how an exploit is performed on a vulnerability. There are a number of sites out there that will host various proof of concepts. Exploit-DB is a well-known one. Also, researchers, once they have identified a vulnerability and alerted the vendor and go through the normal process, the responsible disclosure process, typically those researchers will then release a proof of concept for that particular vulnerability as well. So these are all the vulnerabilities are kind of standardized through the Common Vulnerability and Exposures system. And so these are also known as CVEs. The format is typically CVE, and then the year that this CVE is identified, and then a 4-digit number, which is typically assigned to that vulnerability. I have seen some which are 5-digit numbers. It just kind of depends upon the number of vulnerabilities in a given year. But the CVEs, they're assigned by the CVE numbering authorities, which is made up of vendors. So if there's a vulnerability in a Microsoft product, Microsoft will issue its own CVE with a number for that. Researchers will also have the ability to issue CVEs. MITRE will be able to do it as well, and those are typically reserved and then assigned to it. So MITRE will maintain that master CVE list, and then NIST, with the National Vulnerability Database, will store each of those with a CVSS score and reference. So CVE, like we said, is the common vulnerabilities and exposures, and that's the specific instance of that particular flaw in that particular product with that particular version. There's also CWEs, which is common weakness enumeration, and it's a like it says, more general weakness category. So buffer overflow or remote code execution or something of that nature, something which isn't tied to a specific product or a specific service, but is a more general weakness classification. And then CVSS, which is the score for the severity of that particular CVE. So typically a 9 or a 10 is going to be critical, and then under a 9 you have high and medium, and there's also, I believe, low and info. So a CVE entry will contain the description of the flaw, whatever products and versions which it could affect, which that can get quite long depending upon what the vulnerability is really encompassing. So in the case of shell shock, for instance, shell shock was a vulnerability in Bash, and it existed in lots and lots of versions of Bash. So the CVE entry will list all of the different versions of Bash where the shell shock is exploitable. Some exploits or some vulnerabilities only exist in a specific version. Some have spread over many versions, just really kind of depends. There's also going to typically be a score associated with it, the CWE classification, and the NVD record is the canonical lookup point for that particular CVE. So the vulnerability disclosure lifecycle. So first happens is discovery. So a researcher, vendor, individual, attacker, somebody finds the flaw. It's not necessarily made public. It may be under active exploit. That's what's known as a 0-day. If it's not under active exploit, then it is a vulnerability which has been identified. And if it is a legitimate individual, then typically there's a responsible disclosure process where that researcher will reach out to the vendor and provide whatever information is needed for that particular vulnerability, and will start a clock. And that clock, and there's a lot of people go back and forth on this, but typically it's a 30-day clock. Sometimes you can go with a 60 or a 90-day clock, but you start that clock once you get in touch with the particular vendor. The vendor will then generally verify if that is a vulnerability. And if they acknowledge that it's a vulnerability, then they will have 30 days to patch that particular vulnerability. And so then once they have patched it and it's tested and it secures that vulnerability, they will release that patch. And at that point, the users of the software, the system, will be able to start installing it and securing their systems. However, that patch is also, it's usually going to be publicly available or available elsewhere. And so attackers can start to reverse engineer the patch to see what it's actually trying to fix. So it's a really frantic period at that point. But usually after either the 30-day clock, 30, 60, or 90-day clock expires, or once a patch is released, then the original researcher will typically be allowed to or be able to publish a write-up, proof of concept, the exploit information, everything on that particular vulnerability, and claim credit for discovering that vulnerability. Now, there is a time frame between when the patch is released and when systems have it installed, or all the customers and clients have it installed. It's usually a pretty broad window depending upon what it is. And if it's a difficult to exploit vulnerability, or it's a software which doesn't get a ton of updates, there could be many months or years in between the patch being released and the update actually being installed. But either way, during that time frame, that's when attackers and anybody can potentially exploit that vulnerability. After it's all done, then there's usually a legacy cycle for it. I was just reading an article today where Microsoft is just extending Windows 10 legacy support for another year, and they decided to stop doing that for a while. Windows XP, for instance, I think it was Windows XP and Windows 7, Microsoft stopped support for that. Then there was a very critical vulnerability that came out, and they released patches for it. So that long-term legacy, there could still be systems out there on the public internet or in a network which may still be vulnerable to various vulnerabilities which have been patched or had patches issued many years prior, but just have never been installed. So some of the types of vulnerabilities, there's buffer overflows. And this is really well known, but it's also a really easy vulnerability to accidentally code into your own program or to leave into some software. And again, a lot of you should be familiar with what a buffer overflow is, but effectively you have some input and you allow some, or you have some input space, and you don't do bounds checking or any sort of validation on that input. So when a malicious attacker sends some data which is larger than the available buffer for that, then it exceeds the buffer bounds and can start to overwrite data, inject code, overwrite variables, or things of that nature. One of the more well-known buffer overflow attacks out there was the Morris worm, which was created by Robert Morris back in the 80s. And that was one of the first worms that spread across, at that time it was ARPANET and infected a massive amount of computers there. And it was exploiting a buffer overflow in, I believe it was the Unix finger utility. So they've existed for many, many, many decades, and they still get introduced every so often into various software programs. So why does it happen? No automatic balance checking, like I was mentioning. So an easy way to kind of test this is you create an array of size, say, 10, and then you prompt for some input, and you just grab whatever that input is and try to store it into that array. Well, if the user inputs more than 10 characters, or 9 characters plus a null terminating character, all the rest of those characters may start getting placed into memory sequentially after where it's supposed to go. So if you aren't very clear and straightforward in how you handle input, then you can easily have a buffer overflow situation. There's also a lot of other legacy functions. A lot of these exist in C, which is why C is seen as a dangerous language for a lot of enterprise environments. But string copy, gets, fgets, the fgets is safer, but there are still ways to have a buffer overflow. So you don't ever want to trust that the user is only going to input X number of characters. You want to only grab X number of characters and treat that as the input. Buffer overflows, and we'll talk a little bit later on this week about SQL injections, are very similar, where SQL injections, you can exceed whatever that input field is, and if you don't sanitize your inputs, well, that can cause all sorts of problems. So buffer overflows typically are in compiled code. There are languages which are a lot safer with buffer overflows. It can still happen, but they are not as vulnerable to those types of attacks. So some modern defenses against buffer overflows, there's the address space layout randomization. And these are, the operating systems typically take these mitigations to prevent programs or prevent attackers from walking through memory and knowing, okay, well, if I do this, it's going to go to this exact space in memory. And so that's what that address space layout randomization is doing. There's also data execution prevention, or DEP, which is part of Microsoft Windows, and it will mark specific regions as non-executable. So you might be able to overwrite some of that code, but you won't be able to inject arbitrary commands into it that it then gets run. There's a stack canary or cookie, which is a value which is placed into the stack that if it is encountered, then there's a buffer which was exceeded, and it kind of sets off an alert or an alarm and could crash the program or something of that nature. There's also control flow integrity, so that indirect jumps and returns only go to specific expected locations. So many return-oriented programming techniques could have vulnerability to that. So that control flow integrity kind of protects against that. There's also these related memory corruption concepts. So there's a stack overflow. So the overflow, when you have the stack allocated buffers, which is when you have more information that exceeds that particular stack, and it's closest to the return address hijack scenario. There's a heap overflow, an integer overflow, where, and a lot of you have seen that, where if you go to the maximum value of an int and you add one, well, what happens to the first bit? Well, typically it gets dropped off, but there are some languages which you might be able to exploit that depending upon what it is. Use after free. So if you free up the memory, but the pointer is still pointing to a freed memory location, then that could be a problem. A lot of times that will cause a program crash, but it could still happen. There's also format strings. So a lot of you have used printf, and passing in the specific format strings for whatever data may make a difference depending upon what you're trying to do, and it can cause some problems. So like I had said, some of the useful resources out there, ExploitDB, very, very useful. You can do a search on there for specific CVEs, specific software platforms, specific programs, all sorts of stuff. And there's a lot of times viable proof of concept code up there that you can run on a vulnerable system to see how it actually works. There's the National Vulnerability Database and MITRE, which will have the authoritative source for CVE details, CVESS, linked to the vendor advisories, so on and so forth. Metasploit modules. So we'll be using Metasploit, and there's a ton of modules in there. If there isn't a Metasploit module, someone will probably create it. But a lot of CVEs exist in there. A lot of other kind of proof of concepts exist. So and Metasploit is really easy to use those to try to leverage those particular vulnerabilities. And then whatever you do, obviously you always test it in a lab. Don't test it in the public internet. Don't test it on some arbitrary site out there. And usually what you do, and this is what I've done before, is I had a system which was vulnerable to a specific vulnerability. And so I took a snapshot of that system. I exploited it to verify that the exploit did what it was supposed to do through the proof of concept code. Then I installed the vendor patch, and then I ran the exploit again to see if the vendor patch actually solved that particular vulnerability. In this particular case, it did not. And so then I had to take additional steps. And so I ended up reverting the virtual machine to check to see, okay, is the patch installing it correctly? Or is there something else that was actually causing it? So you want to verify it can be at times a slow and time-consuming process. It's very much a puzzle, a logic puzzle, where you're trying different things to verify that step A leads to step B, which leads to step C. And if something stops halfway through, then you need to identify why and potentially retrace your steps to go through the same process again. So just as a refresher, vulnerability is some weakness. Exploit is the proven working technique. There are CVEs, which is the CVE dash year dash and then some number. There's CWEs, which is a weakness type. The CVSS scores, which can range from 0 to 10. And those are typically assigned to it. The risk from a given CVE spikes sharply once the proof of concept code or the patch is released or an exploit kit integration appears. Buffer overflow attacks, really, really bad. They exist in a lot of stuff. And I mean, I can guarantee you that there are still buffer overflow exploits which are active in the real world right now, vulnerabilities which are out there in buffer overflows. There are a lot of modern mitigations, which are typically at the operating system level. So the address space layout randomization, the DEP, stack canary, CFI, things of that nature. And then you want to validate the public exploit code and make sure that it actually does what it says it does. So you don't want to just say, oh, there's this vulnerability and it's definitely vulnerable to that without testing it, because version numbers are not always authoritative as to that vulnerability existing.